Okay, so today we're going to start off Unit 2, kind of piggyback what many of the things that we did in Unit 1, and we'll talk a little bit about the periodic table in terms of chemical bonding. And we'll use the periodic table to figure out what type of bond might form between two different atoms. So another trend, I guess, is electronegativity, and the general trend is the lowest value going to the highest value. I'm going to erase this in a second, but metals are going to have low electronegativity. Non-metals are going to have high electronegativity. And if you noticed, the noble gas column, for the most part, doesn't have any numbers associated with it because they're not going to try to attract electrons. And that's what electronegativity is, the ability to attract electrons. And someone named Linus Pauling came up with this idea, and he used a number of different things to come up with these relative values. But we're going to use those values to kind of predict if it's going to be maybe a non-polar bond, a polar bond, or an ionic bond. So here's a little bit about Linus Pauling. Very, very famous chemist. He was also in the race for the double helix. His team lost out to Watson and Crick, but in spite of that, he still has 2 Nobel Prizes, and lots of people listened to him because he had 2 Nobel Prizes, and later in his life went through and had some predictions and wrote a lot of different books about taking multivitamins. Well, no, not taking multivitamin, taking vitamin C, taking other types of vitamins. A whole industry developed somewhat because of him. And you can go down to Target and you can have a whole lane of just all kinds of vitamins. But I guess when you win 2 Nobel Prizes, people will listen to you. Okay, so we're going to listen to them in terms of electronegativity. So if you have 2 atoms that come together and they have similar electronegativities, they virtually share the electron or electrons equally, and that's called nonpolar. If one of the atoms shares the electrons, if it has the electrons more than the other atom, so an unequal sharing, it's called polar covalent. And then the third type is if instead of sharing, if one atom loses the electron or electrons and another atom gains the electron or electrons, that's going to be called covalent. And our old friend Coulombic attraction, let's go red pen here. Coulombic attraction is going to come into play again, and not the same method not in the same method we used for the last unit, but we're still going to be able to use that. So we're going to kind of go back and forth here, but here's some kind of questions you might be able to get. By the way, there's a misprint here. I'm not sure where this carbon came in. This is supposed to just be CI. So these aren't necessarily molecules. Definitely they're not molecules, but they're bonds that would be inside of molecules. So it's all carbon with something else. So if we go back and look at the electronegativity values, and carbon's value was 2.5, and let's write that down. So we're going to kind of have to go back and forth here. So carbon has a value of 2.5. Fluorine is 4. Chlorine is 3. We'll grab those 2. Let's check out what else we have. We have iodine and bromine we have to deal with. Iodine and bromine, almost the same value. 2.8 for bromine, 2.7 for iodine. Okay, so what we're going to do is we're going to examine a bond and just subtract the two numbers. And we're always going to go higher to lower. So carbon's 2.5, chlorine is 3.0. So I'm not going to write the math down, but 3 minus 2.5 will give you a 0.5 difference. And the lesser difference will be more nonpolar, and then we'll get a little more polar. And then if there's a tremendous difference, and typically you need a metal and nonmetal for that, and none of these are going to be a metal and nonmetal combination, but if you had a combination like that, like we won't have to look at the numbers, but if we did francium and fluorine, that's the most extreme ionic example, that's going to have a tremendous difference in electronegativity, so it's going to be very ionic. Well, you can't have, once you're ionic, you're ionic. Once you gain or lose electrons, you gain or lose electrons. So carbon and carbon, we don't even have to look at any numbers. Anytime you have two atoms that are the same, they're going to have the same electronegativity, and so the difference of that is going to be 0. That's the only truly nonpolar bond, something that has two atoms bonded together. What was the next one? Carbon and fluorine. We have 4 minus 2.5, so we get a 1.5 out of that. Fluorine, you would expect that. Fluorine with almost anything would give you a very big difference in electronegativity because it has such a high value. We have carbon and iodine. So we got 2.7 minus 2.5. So that's a 0.2. And then we have carbon and bromine, 2.8 minus 2.5. So 0.3. So you just rank those. So increasing order of polarity, this is the least polar all the way to the most polar. And you would rank those. Do these answers correlate with the periodic trend of electronegativity? Well, we can definitely let's look at these 4 atoms. It looks like, I'll draw my little tiny periodic table here, and that was the trend in electronegativity. So it is up and to the right. And if you look at that column of the periodic table, the halogens, so those are the 4 that I check marked, it definitely goes up in value as you go up the periodic table. So let's check out the next question here. Using Coulomb's law, why does fluorine have a higher electronegativity value than iodine? So maybe we better revisit what Coulomb's law deals with. It deals with 2 different charges and radius, or radius squared, but we can talk in terms of radius. So what is going on here? Well, fluorine has a certain number of protons, has a certain number of electrons. So those are our Qs. And yes, as you go down the periodic table, you get more protons and you get more electrons. So the Qs are going to increase, but what increases more significantly is the distance. So with fluorine, fluorine to whatever it's going to bond with, well, no, we don't even have to talk in terms of what it's going to bond with, just its outer electron shell is closer to the nucleus than any other of these halogens that we were talking about. So that's what is going to give it its higher electronegativity value, is this part, the R. Okay, iodine, really, really large atom, so its R value is going to be tremendous compared to fluorine. So its Coulombic attraction is going to be lesser, and that's why it has a value of 2.7 as opposed to fluorine has a 4.0. Okay, I think we're going to try to do this question actually without visiting the electronegativity values that I have on that slide previous. And the reason we're going to try to do this is because you're not going to memorize those values. It's too many values to memorize, and you're not going to be provided a periodic table that's going to have all those values on it. But we do have a trend. Again, the trend is up and to the right. Okay, so nonpolar is a small difference in electronegativity. Those atoms are going to have to be very close together from each other on the periodic table. Ionic, if you remember, I said that's typically going to be a metal and non-metal. So they're going to be very far apart. If you have two atoms very far apart from each other in the periodic table, the difference in electronegativity is going to be very large. And then polar covalent is, going to be in the middle of those two answers. So let's look at ionic first. So are there any metals and non-metals? I'm just going to use I as ionic. So there are two metals here, potassium and cesium, combined with two nonmetals, fluorine and chlorine. So those are going to be ionic. I said the only true nonpolar is going to be if it's bonded to itself. Carbon and carbon, so nonpolar, we'll just go NP. And then we have these other ones here, HS, HC, HCl. Now H is a strange one because H is located on the left-hand side of the periodic table on most periodic tables. But there's a good argument that you could put it in column 7. So fluorine would be right below it. And why can you make that good argument? Because it is 1s1. So it could either gain or lose that electron. So that's why a lot of people kind of consider it in both these columns. So that makes it interesting for electronegativity values. So let's actually visit, I know we said we weren't going to do it, but let's go back and look at hydrogen's value, 2.1. So it doesn't really belong really well with the rest of these metals over here. It actually belongs it doesn't really belong here either where I mentioned it as far as electronegativity. It's kind of a midway point between these two. So you kind of just have to look at these case-by-case basis, and it would be nice to maybe think about that hydrogen has a value of 2.1, which is a little more non-metalish than metal. So you can kind of see here there's a number of non-metals that kind of have around that same electronegativity value. So I know one of the ones we had was let's go back to this. We had H and we had Cl. So 2.1 for H, Cl was 3. So 3 minus 2.1 is 0.9. Now in first year chem, you may have had a cutoff. Hey, if it's beyond this value, it is ionic. If it's between this value and this value, it's polar covalent, so forth. Well, those were nice little rules for first year chem, but they don't exist. They just were there because it made it a little bit easier for you guys in first year chem. But what we're going to do is relative, meaning that if something has a difference of 0.6 and something else has a difference of 0.9, then the 0.9 is more polar than the whatever had the 0.6. Okay? So 0.9, by the way, is polar. But I would say, you haven't seen many of these before, but I've seen more than you have. I would say this is very polar. Not quite ionic. And then H and C, this is going to be, let's go back. I guess we will go back and look at these values to give you guys some context. 2.5 for carbon, 2.1 for hydrogen. So 0.4 for that carbon-hydrogen combination, which is significantly less than H and Cl. And I think we had the other one was carbon and sulfur, 2.5 and 2.5. Wouldn't you know it? Just by happenstance, those are the same exact numbers. So that also will be truly nonpolar. Typically, the only truly nonpolars are going to be when they combine with themselves, but we lucked out here. We got a 2.5 minus a 2.5. So we kind of answered that next question here. Oh, here's another one that's going to be truly nonpolar. And then again, remember we said that the this one lucks out that oh, it's hydrogen. I think I had done carbon and sulfur. Sorry, so we might have to revisit this one again. So I think 2.1 for hydrogen and 2.5 for sulfur. So that actually gives you a difference of 0.4. So that's not going to be as polar as HCl, but it still has some polar qualities. Lower than HCl. So it's relative values. So now that we know if something is nonpolar, polar, or ionic, we also can figure out does it have a dipole? And dipole, that's a prefix 2, di is 2, and then poles. So think of a magnet. A bar magnet may have a positive side and a negative side. That's a dipole. So if you have a polar covalent molecule, like we had HCl. Here's the Cl. These aren't drawn to scale, but there's the Cl. And remember that Cl had a much higher electronegativity value, so it attracts electrons more. So it actually has a partial negative charge, and you can use that term, that symbol, or you could use that symbol. I think my first one might be a little bit easier for you guys, so that's why you can do that parentheses negative. And the hydrogen has a smaller electronegativity value, so it doesn't share the electrons as much, so therefore it's going to have a partial positive charge, dipole. So those are going to be very important because they can attract and repel other things, and that has a lot of significance for physical properties. Okay. So some people designate that dipole in this way. That's the little positive, and then you don't really get the negative part, but a lot of people show it that way. And then you can, we're not doing this, but you can actually look at the angles. This doesn't have, it's just two atoms, so we don't have to look at the angles of that, but you can revisit the angles of the molecule and how much partial sharing of electrons are happening, and you can actually come up with a number, how sort of strong that dipole is. And the picture I took off the internet for water shows that we don't need to know anything about 1.8 dipole. But water is a tremendous dipole, a polar molecule. And why? Because it has an H bonded to an O and another H bonded to an O. So it has, in this bond difference, these electronegativity differences between oxygen and hydrogen is fairly significant. So this partial negative charge of oxygen is very significant. And this partial positive for the hydrogens is also very significant. So it makes it a strong attractive type of polar molecule. And we've studied water. You've studied water for many years in your science classes you've taken, even back in probably even in elementary school, but definitely in middle school. Okay, so I've mentioned ionic, and here's again, we'll revisit this again. But now that we have atoms that come together to make an ionic bond, we then have an ionic compound. And we can use Coulomb's law again, but we'll not call it Coulomb's law, we'll call it lattice energy. Why lattice? Because it's a repeating structure. It's not always 1 to 1 to 1, but it's going to be a repeat. This might be for Na and Cl. Again, not drawn to scale, but they combine in a 1 to 1 ratio, and I could keep going like this as long as I wanted. That's a lattice. It is a repeating structure of positives and negatives in this case. So we still have the Q's, we still have the R or R squared. Remember that this K is a constant. So if we were going to mathematically figure something out with lattice energy, we would need that constant. But this class, we're not doing any math with these Coulomb's law type of ideas. We're just using this as a relative. Something has more lattice energy than something else. So it's going to be about the charges. In this case, here's some charges, a +1 and a -1. And then how far away are these charges from each other? So they're both going to be very important. Okay. You don't know why, because we're not doing the math of this, but I will tell you that we will try to keep it as the charges are more important. If you have to break a tie, then we'll go and look at the distances. So let's see what a question might look like for that. Well, here's a lattice structure, a lot more positive and negatives than I had. Remember that ions have very different sizes. So sodium ions, we'll just go one of these, has lost an entire level of electrons. So it's much closer to the nucleus, the outer electrons. So that's why it's so much smaller than chlorine. Okay? But that's a repeating structure of sodium chloride. That's a 1 to 1. Once you get into maybe like if you did calcium chloride, it won't have this exact same structure. And you can go, not in our class, but you can take other chemistry classes and look much more in depth of how these come together, the geometries of those. Okay, so we talked about covalent. And then you can have different types of covalents. You can have where they would have like maybe, here is one with carbon with 2 electrons between carbons. Now that's not a molecule, but it's a bond. That would be a single bond. And some people typically write it with the 2 dots, or you can go and substitute a line for 2 dots. Double bond, that would be, I'll put it over here. That could be a series of 2 sets of dots or 2 lines. And then triple bond would have 3 sets of dots or 3 lines. And because single bonds only share 1 pair of electrons, there's not a lot of energy associated with that. The distance between the 2 atoms is greater. They're not as stable, meaning it's easier to break those. Double bond, pretty much halfway in between the single and triple. Triple typically are the shortest between the atoms, and they have the most energy. Meaning that if you wanted to break one, you'd have to give it a lot of energy to break one of those bonds. And then and you've learned these in first year chem, but covalent and ionic compounds definitely have different properties. So covalents, not very hard. Some of them aren't even solids, but if they are solids, they're going to melt or boil it very easily. Many of them don't dissolve in water, and then ionic, many of them are going to be opposite of what I just mentioned for covalent. And I think that's it.